Much of what has been introduced into endodontic instrumentation has produced results that weaken the tooth and subject the instruments to increased chances of separation. This should simply not be the case. The last concern should be separation. Canals can be well cleansed without sacrificing the excessive amounts of dentin that are a result of graded tapered instruments. Most ironically, safety for the instruments should never be the reason dentin is removed, yet that is the situation that exists today. This lecture's main goal is to shed light on options that exist today that virtually eliminate instrument separation, preserve far more dentin, and do so in a time and cost-efficient manner. Let's talk about the consequences of the way endodontics is being taught today. We are mainly referring to graded tapered nine-tie instruments used either in continuous rotation or interrupted rotation, otherwise known as non-linear reciprocation. Perhaps the most well-known consequence is instrument separation, leaving a portion in the canal. Here we see examples of separated instruments. They can break in the coronal, middle, and apical third. Due to their fluke design, coupled to rotation, the instruments may break after they have inadvertently been drawn beyond the apical confines of the root. We often think that an apical bind will cause breakage, but as we see in the photograph of an extracted tooth, the canals are not predictably conical along length, often having areas that are constricted. A significantly tapered instrument may quickly bind at these locations, and because of rotation, produce stresses that overcome the elastic limit of the metal, leading to separation. What we are specifically talking about is generally some combination of torsional stress and cyclic fatigue. An example of torsional stress would be the bind that results from engaging and then locking into the tooth structure at unpredictable points of constriction along the lengths of the root. Another cause of breakage is cyclic fatigue. As the name implies, it is a result of repeated stresses to the instrument, none of which alone would cause the instrument to break, but cumulatively lead to failure. An instrument negotiating a curved canal in rotation will undergo a bending motion every 180 degrees, producing repetitive cycles of compression and tension. Binding is not required for breakage, although the combination of cyclic fatigue and torsional stress together make the instrument more vulnerable to separation. When graded tapered instruments are introduced into canals that are typically quite thin in the mesiodistal plane, they not only subject themselves to stresses, but as has been documented, subject the dentin to stresses that result in microcracks. The pulpal anatomy does not fit the method of graded tapered instrumentation being employed. Stresses are increased in the mesiodistal plane, with the broader buccolingual plane barely being touched. Two of the ways suggested to minimize instrument separation is the use of the crown-down approach, where graded tapered instruments are first used to widen the coronal aspect of the canal, and then subsequently lesser tapered instruments are used to negotiate more apically. Another similar approach is the creation of straight line access, thereby reducing the degree of curvature a rotating nine-tie instrument will be subject to. We must realize that both crown-down preparations and straight line access are techniques employed to preserve the integrity of the instruments and are purchased at the expense of the structural integrity of the root. From my perspective, this is putting the cart before the horse, or perhaps more accurately, introducing a problem, namely separation, whose correction produces effects that are adverse to the final result. This schematic clearly shows the increased amount of dentin that is removed to achieve both straight line access and a taper that is less engaging along length. As long as one uses rotating instruments, the need to remove excess dentin as a hazard to instrument integrity remains. We are locked into removing more dentin than we want as long as we are committed to rotation. Eliminate rotation and we eliminate the need for straight line access, crown down preparations, and for the most part, graded tapered nine-tie instrumentation. Ready? Please note that excess tooth structure is removed in the mesiodistal plane because it is the plane that the pulp is the thinnest, often forming isthmuses of tissue rather than the round tapered canals we inaccurately envision in our minds. The pulp is thin mesiodistally because the roots within which the pulp resides are thin. Embryologically, the pulp generates the root dentin, and its shape reflects the original shape of the pulp. This insight should have profound impact on the shaping procedures we use in endodontic instrumentation. Here are some micro CT scans of what the pulp tissue looks like. Please note their long buccolingual dimension, their very thin mesiodistal dimensions, and the significant concavities that exist on their furcal sides. These concavities reflect the concavities that are present on the external surfaces of the roots. When we see these scans, it becomes difficult to rationalize any instrumentation system that encourages greater tapers in the mesiodistal plane or straight line access. The price paid for the safety of the instruments is often too great, compromising both the quality and quantity of the remaining dentin. One might look at the X-ray of this tooth and question the reasons for failure. However, upon extraction, we can clearly see the defect that resulted from excessive removal of dentin mesiodistally that produced a strip perforation and the difficulties in obturation. The latter part of this lecture is to show you how to avoid the excess removal of dentin while keeping the instruments 100% intact. I have alluded to poor cleansing in the buccolingual plane. This should come as no surprise. Using instruments that are vulnerable to breakage tends to make one conservative in their usage. Light-centered strokes produce the conical shapes. To use these instruments laterally with any degree of force increases their likelihood of breakage. Their greater tapers would make it difficult to draw them buccally and lingually into what are often thin isthmus-like pulpal configurations. The use of K-files to first widen these canals buccolingually is likely to impact debris apically, resulting in loss of length. We will show you better ways. Here are some photomicrographs documenting the challenges of buccolingual cleansing, where the pulpal spaces are often thin and isthmus-like, at times partially calcifying, and at other times practically non-existent. Common sense tells us that our best chance of invading these thin spaces is with our thinnest instruments. However, to avoid the impaction of debris referred to earlier, these instruments must be designed to efficiently remove dentin with the lowest potential to drive debris apically. Here we see a photomicrograph of roots, first unprepared and then prepared with various rotary systems. What becomes evident is the centered shaping that rotating niti performs with little, if any, extension of preparation into the buccal and lingual spaces. Furthermore, the centered conical shaping removes excessive amounts of dentin in the mesiodistal plane that communicate with pre-existing external dentinal defects while widening the defects that already exist. This is exactly what we don't want from our instrumentation systems, where preservation of dentin is a primary goal along with the instrumentation of the buccal and lingual extensions that harbor tissue and bacteria. For the most part, most negative comments regarding greater tapered rotating niti instrumentation had to do with the vulnerability of the instruments to breakage. Techniques have been developed to reduce that concern, including the introduction of new heat-treated niti alloys and some degree of reciprocation. Yet a far more serious problem has presented itself in the documentation of the production of dentinal microcracks via rotating niti instrumentation. There are multiple studies today that demonstrate their presence. More recent studies confirm the correlation of microcracks with a decreased resistance to vertical root fracture. While advocates of rotary niti claim these are artifact studies of extracted teeth that have no meaning, the same results are produced when finite element analysis is done. From my perspective, we should also use a bit of common sense observations. We don't need research studies to know that rotating instruments are subject to breakage. If we think about it, instrument breakage occurs because of the stresses imposed on the rotating instrument by the canal walls. After all, they would not break if they were rotating in the air. Given this obvious reality, and given the laws of opposite and equal, first stated by Isaac Newton, is it not altogether likely that the rotating instruments produce equal and opposite forces on the canal walls, resulting in the dentinal microcracks that have been found in so many studies? Here we see two different types of dentinal defects. In the upper photomicrograph, we see external defects that exist prior to instrumentation. Yet the greater tapered preparations are so great in the mesiodistal plane that they generally thin out the tooth structure excessively, and in one case actually create a communication between the external defect and the internal preparation of the canal. In this same photo, please note the inadequate preparation of the canals in the buccolingual plane. Given the fact that it was stated in the study that an experienced endodontist had shaped all the teeth, what we see is likely a typical result of what would be called well-done canal shaping as viewed in the limited vision of a mesiodistal X-ray. The micrograph below simply shows the dentinal defects produced by rotating niti. Rotary niti claims that it produces less debris apically than other approaches. We are far enough along in this lecture to challenge its claim with some simple logic. Rotating niti must have a non-cutting tip lest it auger through a solid wall of dentin. Yet it has flutes along length that draw the instrument apically as it rotates within the canal. The canal is filled with pulp tissue that first encounters a non-cutting tip and is then pushed apically by the drawing in of the instrument. While the lateral dentinal filings are caught in the flutes of the instrument and are wiped away repeatedly via the instrumentation procedure, the soft tissue in front of the non-cutting tip will be driven apically. This has been demonstrated in studies that clearly show increased amounts of debris with greater tapered instruments used in rotation. Again, we will show you a better approach. The same rotating fluted design that draws the instruments beyond the apex will also drive the debris in front of the tip beyond the confines of the root. As the data comes in documenting the production of dentinal defects, rotary niti's advocates continue to state that the research results are anomalies and have no impact on clinical success. Yet, today we now have studies that show a marked reduction in resistance to vertical root fracture after rotary niti instrumentation. There is a general awareness that the recognition of vertical root fractures is on the rise. This is an observation that has been made over the last 20 years, roughly the time since the introduction of rotary niti. The claim that the two may be related is based on an abundance of research that correlates the defects that lead to vertical root fracture with rotary niti instrumentation. Since alternative instrumentation techniques exist that do not produce microcracks, their exploration would be beneficial. When tooth structure is excessively removed in the mesiodistal plane, in teeth where the pulp is very thin in that plane, the roots become weaker. The greater the degree of canal taper, the more the occlusal forces concentrate the masticatory stresses coronally, not unlike a tapered cast post. It simply makes more sense to preserve coronal tooth structure and in the process limit the degree of taper. Once again, the increased taper that increases safety for the instruments weakens the teeth, particularly in the mesiodistal plane. We must get away from canal preparations that are designed for the safety of the instruments. Yet at the same time, we must fully debride the canals in 3 dimensions. Early solutions for reducing instrument separation was and is single usage. Rotation subjects the rotating instruments to an unpredictable amount of torsional stress and cyclic fatigue. Since there are so many variables that can produce excess amounts of stress, the manufacturers determined that single usage was best. Certainly, single usage cuts down on the instrument.
It's okay.
Certainly, single usage cuts down on the incidence of separation, but it does not eliminate it and forces the user into significantly higher costs while underlining the fact that these instruments are vulnerable to breakage and should be used conservatively. Yet, the term conservative does not really apply because they take away too much tooth structure in the mesiodistal plane while barely touching pulp tissue in the buccolingual plane. When we adopt a system that minimizes instruments that can be used multiple times and emphasize instruments that initially are far more expensive and are recommended for single usage, naturally our costs increase significantly. While greater time efficiency has been noted with engine-driven rotary systems, we will be discussing alternatives that are also engine-driven, are quite efficient, but do not limit the user to a single usage. Despite all the modifications introduced after the initial introduction of rotary niti, I have rarely met a dentist who does not comment on the procedural stress he or she feels when shaping curved canals with rotating niti. Many dentists accept this as an unavoidable part of treatment, but that is only because they are not familiar with methods that virtually avoid these stress-producing events. I would sum it up this way. When the dentist must be constantly conscious of the impact of the procedures on the integrity of the instrument rather than the integrity of the root, it underlines the fact that he or she is using a poorly conceived product. And the ultimate irony is that the dentist, for the most part, is still dependent on the original K files that were used prior to the advent of rotating niti for creating the glide path, without which the greater tapered niti instruments would be way too dangerous to use. K files are used manually for the creation of the glide path, producing hand fatigue, and tend to impact debris apically in curved canals, resulting in loss of length before rotary niti is employed. What we are really saying is that we not only need alternatives to rotary niti for all the reasons stated, but we need a more efficient way of creating the initial shaping that is still done with the poorly designed K files. And that brings us to a far safer, more efficient, less expensive approach to endodontic instrumentation that virtually eliminates hand fatigue and separation while preserving far more tooth structure. By substituting 30-degree reciprocation oscillating at 3,000 to 4,000 cycles per minute for rotation, we immediately eliminate all the problems associated with rotary niti. The following slides will make this point with great clarity. Rather than using K files that are designed with a high concentration of horizontal flutes along their shank, we use reamers that have fewer flutes and are far more vertically oriented. The reamers from 15 on also incorporate a flat along their working length, further reducing their engagement along length while increasing their ability to shave away dentin from the canal walls. Looked at side by side, the differences become obvious. Both are used with a watch winding stroke with the occasional vertical motion to bring the shaved dentin coronally. The reamers, however, are designed to be used in the 30-degree reciprocating handpiece immediately after the first instrument has been negotiated manually to the apex. Some of the obvious things you should note include: 1. Far more flutes along the length of the K file that translates into more engagement along length, encountering an increased amount of resistance to apical negotiation. 2. The horizontal orientation of the K file flutes tend to engage and disengage from the canal walls without shaving dentin away, only removing it on the upstroke when the flutes are more or less at right angles to the plane of motion. 3. The greater number of flutes, the more twists that are incorporated, and the stiffer the instrument, an undesirable characteristic of K files. And 4. The excessive engagement along length minimizes the tactile perception of the tip of the instrument as it either enters a tight canal or hits a solid wall. It is crucial to differentiate between the two. Compare the K file design to that of the modified reamer. 1. The vertical flutes of the reamer immediately shave dentin away with the first clockwise stroke, whether it is generated manually or by the 30-degree reciprocating handpiece. 2. Fewer flutes produce less engagement and resistance along length from the start and is further relieved by the immediate removal of shaved dentin. 3. Both the incorporated flat and the fewer number of instruments produce a far more flexible instrument than its K-file counterpart. And 4, with greater flexibility, more efficient shaving of dentin, and less engagement along length, the tip of the instrument produces a far superior tactile perception for the dentist, allowing the dentist to differentiate between a tight canal and a solid wall. To be more specific, the remas have half the number of flutes and are oriented twice as vertically, encouraging easy passage through what might be a tight, tortuous canal. Combined with greater flexibility, the dentist will note how much easier they negotiate the full length of the canal compared to K-files. Once negotiated to the apex manually, even the first instrument, often an 06-tipped, 02-tapered stainless steel reamer, can be employed in the 30-degree reciprocating handpiece, oscillating at 3,000 to 4,000 cycles per minute, with no fear of separation, creating a space where the subsequent instruments will negotiate to the apex with minimal resistance in the vast majority of cases. Please note that because separation is not a concern, we have the freedom to work the instruments buccolingually with vigor, assuring ourselves that we are removing tissue in areas that are often untouched by rotary niti, while still preserving far more dentin in the mesiodistal plane. Distortion is unlikely, since the thin stainless steel reamers are highly flexible and record the curvatures of the canal as they negotiate through them. As the pathway is defined, the subsequent larger instruments follow what is becoming a clearer pathway that is being freed up in both the mesiodistal and buccolingual planes. Taken together, the consequences of greater flexibility, less engagement, and more efficient cutting along length produce a superior tactile perception along length and at the tip of the instrument. Because we limit the arc of motion to 30 degrees, we can afford to employ a cutting tip that dissects through any tissue present rather than impacting it apically. The superior tactile perception tells us when the tip is encountering a solid wall, at which point we would stop apical negotiation, pre-bend the instrument, and manually negotiate around any obstacle that might be present. Once around the impediment, we would reattach the rema and negotiate to the apex. In this way, we can negotiate the most curved canals without distortion, without losing length, a problem that K-files have had since their introduction so many years ago. It is important to appreciate the fact that a 30-degree arc of motion generated in the reciprocating handpiece is 1/12 of a circle, or 5 minutes on the face of a clock. That is an extremely short arc of motion that does not generate significant amounts of torsional stress or cyclic fatigue. The short arc of motion allows for a high frequency of motion of 3,000 to 4,000 cycles per minute that provides for time-efficient canal shaping. From the start, a 30-degree reciprocating system obviously eliminates hand fatigue from the beginning of the procedure, with the added assuredness that separation is virtually a thing of the past. Please note that the handpiece is a receptacle for hand instruments. In fact, any one of the instruments can be used manually, but they are used so much more efficiently and safely in the handpiece. Once one gains the confidence that the instruments truly remain intact, even when used aggressively against the buccal and lingual walls of the canal, the dentist will be comfortable using them in the reciprocating handpiece immediately after gaining length measurements. Here is a video showing the short arc of oscillation. Revving up to 3,000 to 4,000 cycles per minute allows full shaping of most canals in a matter of a few minutes. This is one of the harder concepts for rotary niti users to appreciate. The entire evolution of rotary niti is one where the dentist had to overcome his or her fear of separation. We are now familiar with the techniques that are employed to reduce breakage, and as the research shows, it has a great potential to harm the integrity of the root. The dentist must realize that 30-degree reciprocation is an entirely different animal. Even though it may vibrate in the hand in a similar fashion, minimal stresses are being generated in the instrument and most fortunately in the root. A 30-degree arc of motion virtually eliminates torsional stress and cyclic fatigue, in turn eliminating instrument separation and dentinal microcracks. Far less tooth structure is sacrificed in the mesiodistal plane. I don't remember. Rarely, if ever, do we exceed an O4 taper, thus preserving dentin in the mesiodistal plane while removing more tissue in the buccolingual plane, nor is straight line access necessary. We have greater debris removal in the buccolingual plane because of the advantages modified reamers driven by a 30-degree reciprocating handpiece oscillating at 3,000 to 4,000 cycles per minute provide. Look at the isthmuses joining the canals in these mandibular molars without even considering the curves in one or more planes. Nothing could be less useful than the introduction of a wide conical shape that removes excess tooth structure mesiodistally while having minimal ability to invade the tissue-laden buccal and lingual extensions. 30-degree reciprocation, predominantly using O2 tapered stainless steel relieved reamers, are a far more rational approach to thorough cleansing and shaping of the canals, with the concurrent goal of preserving as much tooth structure as possible. To date, the studies of dentinal microcracks during instrumentation are associated with greater tapered rotating Naitai instruments, be they continuous or interrupted. Short arcs of motion, even oscillating at 5,000 times per minute, did not produce microcracks, nor did hand instrumentation. It is reasonable to assume that without such defects being produced, the long-term prognosis against vertical root fracture must be better. Retaining more dentin and being free of defects would certainly seem a safer way to go. Given the state of litigation in this country, it makes sense to take the safest route and inform the patient in the process. Lesser tapered preparations, making the tooth more resistant to masticatory forces, also make sense. Do you remember the old days when it was normal to use the instruments more than once? That is what sterilization is all about. The fact is they can be used safely multiple times, and the downside to overusage is a dull instrument, not a separated one. I would routinely recommend using these instruments on average about 5 to 6 times before replacement. Multiple usage and low cost to start with makes these instruments far less expensive than rotary systems, while being far safer. That is really the point that should be emphasized. The only way you will experience less procedural stress is by trying the approach we advocate. You can then compare and decide what works best for you. I want to emphasize the following. These instruments faithfully follow the glide path created by the most flexible O2 tapered stainless steel reamers. Again, one must try them to be completely convinced. We already covered this, but it is worth repeating. The reciprocating relieved reamers push far less debris over the apex because of a cutting tip and not being drawn into the depths of the canal. With a motion that does not allow for being drawn in, the dentist has superior measurement control. Here's a case I finished a few weeks ago. I thought it represents much of what I'm trying to convey, including the ability to shape canals without removing excess amounts of dentin, preserving canal anatomy, and excellent measurement control without the accompanying concerns of instrument separation and the increased possibility of dentinal defects and excessive removal of coronal dentin. The sequence of instruments used to produce these results is straightforward. We create a glide path through 20, starting in highly calcified canals with an 0.6 millimeter tipped O2 tapered stainless steel reamer, first negotiated to the apex manually, and then used in the 30-degree reciprocating handpiece, sitting at 3,000 to 4,000 cycles per minute, to widen the canal sufficiently for the next instrument in the sequence to negotiate to the apex with minimal resistance and making the procedure a rapid one. It should be noted that starting with a 15, the reamers incorporate a flat along their working length, increasing their flexibility around a curve and reducing the engagement along length, allowing them to reach the apex while encountering less resistance. All the instruments that can possibly be used are presented here. Typically, we create the so-called glide path by shaping the canal through a 20. Our minimal goal is to produce a shape that mirrors the original anatomy in larger form, be it round, oval, or highly isthmus-like. To attain that goal, after shaping the canal to a 20, we take our 3004 relieved NiTi instrument and take it within 4 millimeters of the apex. We follow that with the 3002 relieved stainless steel reamer to the apex, at which point we can now fit a fine point with an approximate 03 taper. If the canal is sufficiently wide, we can now take the 3004 to the apex and fit either a fine or fine medium point to the apex. The rest of the instruments in the kit are designed to open the canal to the apex to a 40 and create tapers as wide as an 08, including a tapered piezo that can be used to widen the coronal aspects of canals that are quite wide and round to begin with. These instruments are rarely used in the mesial roots of mandibular molars and the buccal roots of maxillary molars. The pulpal tissue in most bicuspids is quite thin in the mesiodistal plane and wide in the buccolingual plane that once again would limit the use of thicker and greater tapered instruments. Rather, here too, thin O2 tapered relieved stainless steel reamers would vigorously work the buccal and lingual extensions of these canals, creating spaces larger than themselves with the end goal of producing a space that mirrors the original anatomy in larger form.